Okay, so let us begin. So last time when we talked about the numerical method and iterative method to compute the eigenvalue of a matrix, right? Especially the largest eigenvalue of the matrix. Right? So what we did is we assume that the initial value is alpha 1 v1, alpha 2 v2 up to alpha n vn, right? And then we come up with a formula like this, and then from this, because absolute value of this goes to 0 as r goes to infinity, we say that xr will goes to a constant multiple of the vector, right? So v1, right? So we proved right? So we proved this part. Right? So what we proved is we proved this, right? By right, so we show this, right? So we show that norm of CR where CR is this term, right? Minus alpha 1 v1 will goes to 0 as r goes to infinity, and by using that, we show that XR will convert to a constant multiple of v1, right? So we showed that part first. Right, so today what we are going to do is, so that basically gives you the results that the sequence of vectors which we derive from this method converges to the leading eigenvalue, eigenvector of the leading eigenvalue, right? The constant multiple of the eigenvalue. Right, so we see that. So next what we are going to do is we are going to show that the sequence KR will convert to lambda 1. Absolute value of KR will convert to absolute value of lambda 1 as R goes to infinity. Right? That is what we want to show. Right?
Excuse me, sir. Sir, board is
Yes.
not clear.
What is not clear?
Yeah.
Okay. Please open your camera. Is it okay now?
No, sir, not. Still not clear.
Is it okay now? Is it okay now?
No,
Still not clear, sir.
the board is
Still not clear?
Yeah.
So just let us know whether it is not clear for all of you or not only one of you.
I think most of us, sir.
So who is the battery?
Yes, sir.
Yeah. What about you?
I'm also not clear, sir.
So not clear means is it blurred or the
Yes, sir,
light
blurred.
is not enough?
Blood, sir. Body is blood.
Right. Okay. Let's try. What about now? Hello, Anuka?
Yes, still it is blood, sir.
Still,
Yeah, we cannot see clearly those small indications.
in our screen, everything is okay. Okay, let's try. What about now, Anuka?
So small letters are not clear to me.
Small letters.
Yes, sir.
But the sharpness is okay, right?
Is this somehow blurred? Not that right.
Are you using your mobile phone?
No, sir, my laptop.
Laptop.
Now it seems okay, sir.
Now is it okay?
Yes, sir. Now it seems okay. Yes, sir. Now we can see.
Okay.
Okay.
Okay. All right. So this is what we did last time, right? So we showed that the sequence XR converges to the constant multiple of the eigenvector associated with the leading eigenvalue by showing this one goes to 0. So next what we are going to do is we want to show, right? Okay, so next we want to show this. We want to show that KR will goes to absolute value of lambda 1 as R goes to infinity. That is what we wanted to show, right? So we will start showing this by using this property. Okay? So we will try to show this. Okay, so since we have this, right, I'm going to use the definition of convergence first. Right, so this is the way to write down the convergence, right? So when you say a sequence converges or when a known converges to 0, that means after certain value of n, right, the index, the component is less than epsilon for some small epsilon, right? So in that case, right, so we can show that for every epsilon, or we can write it as for every epsilon, so and so. But by using the norm property, right, so this says, so absolute value of right, so for all r greater than n, absolute value of norm of CRXR minus norm of alpha 1 V1 is less than epsilon, right? So this leads to minus epsilon less than CRXR, so that is absolute value of CR times norm of XR minus absolute value of alpha 1 times norm of V1 less than epsilon, right? For all r greater than n. Right? So you get rid of the absolute value part, so you will end up with this, right? So that is, right, so there exists n belongs to natural number such that, right, so what you have is this. Okay, so when you rearrange this inequality, you move this alpha 1 norm of P1 on this side and this side. There are two inequalities there. So you move, so basically you add alpha 1 P1 on both sides, and then because CR is positive, you can, sorry, XR is positive, you can divide by XR. So you ended up with this, right? So this says, for any r greater than n, this one is true, right? So then for n and n plus 1, everything is true, right? So you know that alpha 1 v1 over x to the power n, right, is less than CR, so I can say Cn, that is Kn minus 1 all the way up to K naught over lambda 1 to the power n, right? So that is what our R or n, right? And then this is less than alpha 1 v1 over normal n. Right? So for any R strictly greater than n, right? So you can show that, or you can write it that this inequality is true. Right? So there is no harm in putting greater or equal to n here. So let's say put greater or equal to n so that you can start with n. Right? Otherwise, you start with n plus 1 and n plus 2. Right? So that's not a big thing. Now the result is true for n plus 1 as well. So then alpha 1 norm of v1 over norm of x to the power n plus 1, right, is less than, Kn up to K naught over lambda 1 to the power n plus 1, right, is less than alpha 1 times norm of v1 over norm of x to the power n plus 1. Right, so you have this two results. So because this is true for all r greater or equal to n, you say it is true for n, then it is true for n plus 1, right? Two successive terms. So I write it for n and I write it for n plus 1. But you know that this one is same here and here, right? And similarly, this one is same here and here, right? At the same time, right? So when you divide this, right? You can see that when you divide this by this, right? So basically, right? So because you choose n very large, right, and you already know the sequence xn is converging to a limit, right? So for certain large n, right, the successive terms are going to be close enough, right? So when n gets larger, the terms xrn and xn plus 1 are going to be close enough, right? Actually, I can say approximately equal to, but whenever you choose large n, you can say they are almost equal because they go to the same limit, right? So in that case, so here the difference here between this and this is this multiplied by kn over lambda 1 is the difference, right? So this one, you have kn minus 1, k naught over lambda 1 n. Here you know kn up to k naught over lambda 1 n plus 1. So the only difference is the second part is multiplied by, from the first part, when you multiply by kn over lambda 1, you get the second part. But you know that the upper limit and the lower limit does not change even if you increase the size of the middle part, right? So that means the size, the term you multiply in the middle part must be close to 1, right? Right, so I can say equal. So that means for large n, kn over lambda 1 should be equal to 1, right? So then only you can say that even if you multiply, increase this middle part by multiplying some kn over lambda 1, you still don't get any increment, right? So that can only happen when you multiply by 1, right? So for any other term, you will have a difference in the value, right? It may increase or decrease. But here it says there is no difference, so then obviously they must be equal. So that concludes the proof, because when n gets larger, right, kn over lambda 1 goes to 1. Right? So when n gets larger, this is equal to 1. So that means when r gets to infinity, kr over lambda 1 must goes to 1, right, as r goes to infinity. So that means absolute value of kr will convert to absolute value of lambda 1 as r goes to infinity. So that is how you compute the leading eigenvalue and the leading associated eigenvector. So that is how we prove the convergence of the power method, right? So this method, we call this as a power method, and we do the example. We prove the convergence of the sequence of vectors to the eigenvector and the convergence of the absolute value of the constants to the spectral radius, that is the absolute value of the largest eigenvalue, right? So that is what we prove. So now what we are going to do is we are going to see an example of this result. So let's say how we can apply this power method. And so let's say, so when you want to apply this, you know you have to have a matrix, right? So it's minus 2, 3, 1. 1, 0, 1. Right, so let's say a matrix A is given, right? Right, so by using this initial value x naught is equal to 1, 0, 0, let us say we apply the power method to compute absolute value of lambda 1. And so I will show you a couple of steps, and then the rest you can work accordingly. Okay, so if you write it in this table form, then it is easy for you, right? So you know x naught is given. So I did this similar type of example earlier as well. Right? So 1, 0, 0 is your x naught. So what you do is, next step, you compute ax naught. Right? So then you compute ax naught. So you have a, you have x naught, so you multiply and write down what is ax naught. Then you multiply, you know you will get minus 2, 3, 1. get a x naught, sorry, ax naught, you can compute k naught, because theoretically k naught is the term with the largest size, the largest sized component in the vector ax naught. So here you know your k naught is 3. So once you compute k naught, you can find x1. So you can find x1. That will be 1 upon k naught times ax naught according to the theorem. Right? So then it is minus 2/3, 1/3. Right? Because you remember this is your equation, right? X r plus 1 upon kr into axr. This is your equation. So when you put naught, r is equal to naught, you get x1 is equal to 1 upon k naught into ax1, then x2 is equal to 1 upon k1 into ax1, and so on, right? So this is how you try to compute the terms, right? So you get x1. And then once you get x1, you know you get ax1. And so the a is here, x1 is here, so you can do the multiplication, right? So when you multiply, you can get the terms, right? So a x1. And so minus 2/3. So you do the calculation, I will write down the answer. And so ax1 is 3 minus 8/3 and 0. Okay, so this when you multiply, you get ax1, that is 3 minus 8/3 and 0. So in this, you have to pick the maximum value, right? So when you pick the maximum value, you know here also it is 3, right? So x1 is equal to 3. The maximum sized component, right? So sometimes it might be a minus number as well, but you pick the maximum size component. So here you get 3 again. And then once you get 3, then you can get x2. And x2 is 1 minus 8 upon 9, 0. Right? And then you get ax2. And you can keep on continuing like this. Right? So ax2, then you get k2. And then you get x3, and then you get ax3, and then you continue like this. So in that process, you will get a sequence k, and you will get a vector xk, xr, right? And then you can see xr is converging to a certain value, right? So you try to see it will converge to 1 minus 1. Okay, so when you do few steps, right? K3, x3, x4, x5, and things like that, and k0, k1, k2, k3, k4, you can observe that this kr will absolute value of kr according to the theory or theorem. You say that absolute value of kr converges to 3, absolute value of 3, and then xr you can see that it converges to 1 minus 1, 0. So that is how you get the absolute value of this and this. So from this, the question is find absolute value of lambda 1. So then, you know, so that is clearly 3, right? Absolute value of lambda 1 is 3. Right. So from this, if you want to get the largest eigenvalue, right? So if you want to get the largest eigenvalue, then this is how you can get this. right? So this is some extra work. Okay, so if in case if they ask you to get the largest eigenvalue itself, right? So not the absolute value. If they want you to pick whether it is plus 3 or minus 3, then how you can pick this? That is the next question. Right? So first one, you get the absolute value of lambda 1 by this. So that is 3. It's understandable. But when you remove the absolute value, you know lambda 1 is plus 3 or minus 3. So you want to make sure which one is correct, plus 3 or minus 3. Right? For that, what you have to do is, because you have this x, right? So let's say x with or v1 I say, and 1 minus 1, 0 is my v1, right? So that is the eigen vector, right? So let me write it down, v1 here, right? So this you can name it as v1, right? So I can name it as v1. Then what I do is I do a times v1 is equal to what? But you know, you should have a times v1 as lambda 1 times v1, right? So that is what you should have, right? So then you can find a times v1, right? A is this, v1 is 1 minus 1, 0, right? So when you multiply this, you know that minus 2 minus 1 minus 3, 3, here 3, and then 1, 1 minus 1, 0, 0. Okay, so to make sure whether lambda is plus 3 or minus 3, right, you have to have this, right? So you find a times v1. So you have a and multiply by v1, so you get minus 3. That should be equal to lambda 1 times v1, right? So v1 is 1 minus 1, 3, 1 minus 1, 0. From this, if you want to get minus 3, 3, 0, you know that it should be this. It should be minus 3 times 1 minus 1, 0. This one, 3 minus 3, 0. So minus 3, 3, 0. Is equal to minus 3 times 1 minus 1, 0. So you have a times v1 is equal to lambda times v1. So this is obviously lambda 1 times v1. So my lambda 1 is minus 3. Right? So this is some extra work you can do, right? So this is basically equal to lambda 1 v1. Okay, so that is how you compute lambda 1. So this is an example of how you can apply this power method to compute the eigenvalue, largest sized eigenvalue and the corresponding eigenvector as well. So now what we are going to see next is, in this method you can see that you compute x naught, given x naught, you compute ax naught and then k naught, and then you compute x1 and then ax1, k1, x2, ax2, k2, x3, like that. In that order you keep on calculating the term. So in most of the cases, you might see in some other examples, you might see that it is, the convergence seems to be slow, right? So it takes many steps to get the results, the convergence, right? So it might take 50, 60 steps for some large examples to see what should be the lambda 1 and what should be the V1. Right? So next what we are going to do is we are going to see how we can speed up the convergence process. That is called Rayleigh quotient technique. Right, so this technique is called Rayleigh quotient technique. So in order to find the technique, first we have to define a Rayleigh quotient, right? So a Rayleigh quotient is always associated with a matrix and a vector, right? Right, so x summation ax over x summation x is known as the Rayleigh quotient, right? So if a vector x is given, non-zero vector x is given, and a given matrix A, which is an n cross n matrix, right? So then we call it as the Rayleigh quotient as x summation ax over x summation x, right? So that is what we call as a Rayleigh quotient. Okay, and then so this is the definition. Then maximum among all possible Rayleigh quotients associated with the matrix A is actually the largest size eigenvalue, right? So it's lambda 1. So you can prove this, right? So right, so if you find the eigenvalues of A minus lambda 1 I, right, then those eigenvalues are lambda 2 minus lambda 1, right, and lambda 2 minus lambda 3, lambda 3 minus lambda 1 all the way up to lambda n minus lambda 1, right? So clearly all these eigenvalues are non-positive, right? Because you know that you have the eigenvalues written in the non-increasing order. So in that case, you know they are non-positive as well. So if they are non-positive, then you know that because of negative semi-definite definition, right? For all non-zero vector x, x Hermitian times the matrix times x is less or equal to 0, right? Because all the eigenvalues are non-positive. So from this, you can see that okay, so from this, if you simplify that, you get x Hermitian Ax over x Hermitian x is less or equal to lambda 1 for all x non-zero. Right? So for all x non-zero, you have x Hermitian Ax over x Hermitian x is less or equal to lambda 1. So obviously, the maximum will be equal to lambda 1. Right? So that is how we say that for a positive Hermitian matrix, you have this to be lambda 1 is maximum of x Hermitian Ax over x Hermitian. Right. So now what we are going to do is we are going to see how we can implement this Rayleigh quotient idea into the power method, right? So which we show already, right? So we are going to implement the power Rayleigh quotient into the power method. So Rayleigh quotient and how we can improve the power method, right? Rate of convergence in the power method. So note that right? So this is what we do in power method, right? And so you know that when x naught is given, what you do is you apply the power method, and at each step you compute a vector xr, right? So given x naught, you compute x1, and you compute x2, and you compute x3, and so on. So at each step you have a non-zero vector computed. So, but you know that A is already there, right? You have a different vectors at each step, non-zero vectors. So at each step you can compute the Rayleigh quotients as well, right? right? So at each step in the power method, we can also compute this one, right? So mu r, which is the Rayleigh quotient at the step r step. Right? So you can always compute this, right? The Rayleigh quotient. So now by using the Rayleigh quotient, what we are going to do is we are going to see that whether the Rayleigh quotient help us to increase the rate of conversion or not, right? So we are going to see this, right? So in order to see this, let us go back to our power method. So where we simplify the power method in the following form. Okay, so let us recall that. So let us see. Right, so this is something we have by using the power method, right? So you know that Kr up to K naught divided by lambda 1 to the power r plus 1 is equal to this alpha 1 v1 plus summation of this, right? So we have seen this. So I can rename this as this. So I name this as epsilon r, right? So then I have Kr up to K naught divided by lambda 1 to the power r plus 1 times x to the power r plus 1 is equal to alpha 1 v1 plus epsilon r, right? So you know you have a new notation here, epsilon r, where epsilon r goes to 0 as r goes to infinity. And so we just rewrite them in a different notation, with a different notation. Right? So that's the only thing we need. Okay, so then right, so when you rewrite this for x r plus 1, right? So that is lambda 1 to the power r plus 1 over K naught all the way up to Kr times alpha 1 v1 plus epsilon r. Right, so you have this, and alpha 1 v1 times this. So you can write this as x to the power r plus 1 is equal to beta times v1 plus epsilon. Right, so you rewrite this again, right? Xr plus 1 is equal to beta times v1 plus epsilon. Right? So you have written the vector XR in a simplified form, right? Also note that epsilon R goes to 0 as R goes to infinity, right? So because epsilon R goes to 0, so epsilon goes to 0 as R goes to infinity, and alpha 1 is a non-zero constant. Right? So that is what we can have from the power method, right? So far we only rewrite the power method in a different way, right? So we have the vector XR plus 1 computed in terms of beta, V1 and epsilon, right? So those are some new notations we have. Right? So right, so now what we are going to do is we are going to compute the Rayleigh quotient, right? Okay, so you compute the Rayleigh quotient. The notation I use is mu, so it becomes mu r plus 1, right? So that is xr plus 1 Hermitian A times xr divided by xr plus 1 Hermitian times xr plus 1. Right? So that is the Rayleigh quotient. But you have a formula for xr plus 1. So I am going to simplify that, right? So mu r plus 1 is equal to beta times V1 plus epsilon, right? Hermitian times A times beta times V1 plus epsilon, right? Over beta times V1 plus epsilon, Hermitian A times A times this times beta times V1 plus epsilon. And so this is your mu Rayleigh quotient mu r plus 1, that is xr plus 1 Hermitian times A times xr plus 1 divided by xr plus 1 Hermitian times xr plus 1. So now you just simplify this. If you simplify this, you know, beta cancelled out, right? So they are constants. So you can cancel out and then you can multiply everything through. So when you do that, you know V1 Hermitian A times V1 plus V1 Hermitian times A times epsilon plus epsilon Hermitian times A times V1 plus epsilon Hermitian times A times epsilon over here, you know, you have V1 Hermitian V1 plus V1 Hermitian epsilon plus epsilon Hermitian V1 plus epsilon Hermitian epsilon. Okay, so you have this. Right? So you have V1 Hermitian A V1 and so on, right? So this is the Rayleigh quotient you have, right? So now you want to simplify this Rayleigh quotient. So if you want to simplify this Rayleigh quotient, you have to see what is this, what is this, what is this, and what is this, right? So first we try to find out a couple of things, right? So before simplifying this, let us try to see the property of the eigenvectors. So this is the orthogonal property, orthonormal property of the eigenvector. Right? Because B1, B2 up to Bn are eigenvectors, right? They are mutually orthonormal. So when you multiply Bi Hermitian with Bi, you get 1. If you multiply Bi Hermitian with any other Bj term, then that will be 0. Right? So this is one of the interesting properties of eigenvectors which we are going to use to simplify this. Right? So in order to simplify this, we are going to see these two. Right? So I am going to leave it as a homework. Right, so you try to compute what is B1 Hermitian epsilon and B1 Hermitian times A times epsilon. Right? So you try to compute both of them. Now you have a formula for epsilon, right? So epsilon is 1 upon epsilon r. So let me just simplify this. Times 1 upon alpha 1 times epsilon r, right? So that is, you can put the 1 upon alpha 1 outside. And then B1 Hermitian times epsilon r is this, right? You know, this is summation of I is equal to 2 to n alpha I lambda I over lambda 1 to the power r times Bi. Right, so this is your epsilon r, right? So V1 Hermitian 1 upon alpha 1 times epsilon r, but 1 upon alpha is a constant, so you pull that out. So you ended up with V1 Hermitian dot summation of I running from 2 to n, right? Alpha I lambda I over r plus 1, I think that is what, right? R plus 1 times Bi. So now you can multiply this V1 inside of each of these Bi's. Right? V1 times V2, V1 times V3, V1 times V4, and all of them are there. Right? But you cannot have, you will not have V1 times V1 there. Right? So all of them are V1 times V2, V1 times V3, and V1 times V4, all the way up to V1 times Vn. But because of this property, all of them will be 0. Right? So clearly you can say this is 0. Right? So if this is 0, then you know epsilon Hermitian times V1 is basically V1 Hermitian times epsilon Hermitian. So that is also 0. Right? If this is 0, this one is 0. Similar kind of argument, I leave it as a homework. You try to show that this one is a 0. Right? And this one is 0, and similarly this one is 0. Right, so these two, I leave it as a homework, similarly. Right, so if you show one of them is 0, the other one is automatically 0. So if you show all of them are 0, then you can simplify this Rayleigh quotient, and then you can see that this one also converges to lambda 1. Right, so that we will prove in the next class. Right, so this is the homework. Now once you figure out that this one is also 0, then this turned out to be a very simple formula. So in the next class, we will try to start with that simple formula and try to reduce this and prove that this Rayleigh quotient also converges to lambda 1, and then we will see the rate of convergence and the examples. That we will see on a next class, that will be at Wednesday 2 o'clock. So I will stop here and continue on